Okay, maybe I should open the chat window. Okay. Chat, okay. Okay, so let's resume. So I'm gonna first briefly give again a very short, quick, sense of where we are. Like we are pretty much at the last lecture today. So today we'll be talking about deep reinforcement learning, which is, I guess, the intersection of RL idea that we saw last time, in particular Q learning, and we're gonna extend that so that it can use a neural network in between as it tries to learn good policies. So basically, learn good actions that can maximize cumulative reward. Okay. So that's the scope for today, and there's three buckets of things that we'll look at. One is called function approximation, which is where, hey, here's a Q learning table. That's, we kind of had a table view last time. We're going to extend it to non-table view. And then we'll look at two case studies. One is called DQN, which is the extension of Q learning, and it's part of your assignment. Question number 3. It's already implemented, so that's actually good. So you can actually look at the code and you can spend more time on tinkering with it. And then the second part will talk about a slightly different application for this Go playing software, AlphaGo, and we're going to discuss the one from 2016, but there's so many new improvements now. But I think it's a good example to kind of get a sense of how RL can impact not just games, for example, which has been the context so far. So that's the scope for today. So where are we in terms of the schedule? So we are here. So this lecture, and then next week is the assignment is due. It's basically just using DQN with card poll, and it's actually already pretty much set up for you. You just have to do sensitivity analysis, okay, which is kind of easy. But I would say since it's made easy for you, and it's made easy because you want to spend more time on the project, but since it's made easy for you, try to tinker around with the DQN algorithm itself or the other algorithms in that repository. Okay, so there are other techniques in that minimal RL repository, to try to use them. And we'll have the meetings, separate meetings next week, and then 2 weeks from now, the project concludes, right? So that's a big component of your course. So try to put as much effort as you think is right for this, okay, compared to the assignment grades, for example. Yeah. So yeah, I just briefly mentioned this last question is what we're going to cover today. So you can look at the code, and the code actually has other algorithms implemented for the same environment, card poll environment. So you can try them out as well to get a sense of how they, I mean, for example, this reinforce algorithm, it's just a very short, it's pretty much, it's just a 20-line code, right? So you should be able to get a sense of what reinforce algorithm does by just looking at the code, for example. So I would say try it out. Actually, the number of lines is actually given here. Reinforce has the shortest 60 lines of code. What we'll see today, DQN has extra things, and we'll talk about them today. Okay, but it's a good repository to get a feel for like other algorithms if you're interested. Okay, other solution approaches. Okay, so before I switch over to the slides, just to recap, we'll look at, we kind of understand the role of function approximation in Q learning. Q learning is just one approach. Function approximation makes sense for other approaches as well, but we look at the role of function approximation for Q learning, and then there are going to be couple of extra ideas. They're not earth-shattering ideas, but they're important to kind of build this DQN model and so that it actually performs well in reality. So there are a couple of innovations, and we'll kind of visit them. Then we'll look at we'll switch gears and actually not look at reinforcement learning problem itself, but a planning problem. Okay, so a planning problem, as I said last time, if you recollect, solving an MDP is a planning problem where you've already been given the states, actions, next, transition probability function and reward function, and they just ask you to compute a policy. That's a planning problem. We'll look at a slightly different planning problem, and for that, it's called the forward search problem. And for that, there's a technique called Monte Carlo tree search, which is quite popular. And so we'll look at that approach, and then that plus all the RL stuff that we saw, deep RL stuff, is going to be part of a solution for this technique for this algorithm called AlphaGo. Okay, and so we'll kind of, so it's just a case study, so we'll kind of not go into too much details. There's a paper in journal called Nature from 2016, which kind of talks about much of the details, but we'll kind of get a sense of how RL and supervised learning also play their role in building that solution. Okay, and also of course this research idea. So that's the goal. So the goal is really three things: function approximation, how does DQN work, and what is forward search, and Monte Carlo tree search is an example there. Okay. Yeah. Okay. Okay, so we'll start with function approximation and then talk about the two case studies. So let's briefly recap the Q-learning idea. So, and this is just an informal motivation for recollecting. Q-learning has a specific template, right? So it says, hey, explore and exploit with some probability given the current Q table, and then there's a particular Q value update equation there. And I'm just going to briefly motivate again how that equation can come, because there's this notion of a Bellman optimality equation. We didn't prove it, but or we didn't fully substantiate it last time. We just said, hey, there's a Bellman expectation equation which is easy to derive because it's just a recursion equation. But the optimal value function also satisfies what's called the Bellman. The optimal value function satisfies a similar equation called the Bellman optimality equation. Okay, and it's not a linear equation. It has a max in its expression. Okay, so it's a nonlinear equation, but it relates optimal values at some other state action pairs to optimal values at some other state action pair. So that's how they are a system of nonlinear equations. Okay. So what we kind of suggested, and we saw that even for the planning version of the problem, when you're solving the MDP problem, you can have what is called a Q value iteration algorithm. Okay. So how do people come from these equations, which are just formula, to a algorithm in this case, is that they kind of convert that equation to an iterative procedure. And the way you do it is you say, hey, okay, I know that Q star satisfies these types of nonlinear equations. I don't know Q star, so I'll start with some random Q star numbers for every state action pair, for example, and then I'm going to evaluate the left hand side, and once I evaluate the left hand side, I'll get new Q stars. So I'm just going to evaluate the right hand side, and I'll get some new Q stars. So I started with some random ones, evaluate the right hand side, I'll get some new Q stars, use those new Q stars, evaluate the right hand side, and I'll get some new Q stars, and so on. Okay, so that's an iterative approach, and folks have shown that actually converges to the true Q star. Okay, so that's a non-trivial result also, but not in the scope of our discussion. But if you just wanted to solve for Q stars given the MDP, that's called Q value iteration, which is exactly what I said, and so that iterative approach works. And so the Q learning algorithm, with the word learning there, is for the reinforcement learning setting, because you don't know the transition dynamics or the reward function. Okay, so you will do the template that we saw last time, which is with some epsilon probability, you'll explore and exploit, and then you do a particular Q value update. Okay, so that update also can be motivated briefly, at least informally, using the Bellman optimality equation. Okay, so in particular, what we're going to do is relax, again start with this equation and then do a couple of changes. Okay, so in fact, one of the changes again going to be iterative. We're going to change this equality to assignment, and then we are also going to drop this expectation, because we don't know the transition, we don't know this P, right? That's what reinforce. We don't know. We have to learn. We don't have to learn, but we don't know P. Okay, what we want to still get is a good estimate of Q star. So we drop this equation and the summation, and so that's what sampling means, I guess. You only know one path instead of knowing all the possible states you can reach from the current state, a little less, for example. And you also make it incremental, which is exactly what we discussed. You kind of drop this equation and try to focus on the right hand side first, and you try to evaluate that. And then, of course, next action also you have to deal with it. You have to do exploration exploitation, because it's a version of a bandit style problem, not a it's not a completely offline problem where you know the reward functions, for example. Okay, so we saw these slides last time. I'm just recapping the two places. If you start with the Bellman optimal equation, there are a couple of places where things change, and that's what kind of leads to the Q-learning update. So let me not look at this one because this is this is basically similar to what we saw here with these two changes. But let me directly get to the Q-learning update. So the Q-learning update is basically saying start with some random Q values. Because you haven't interacted with the environment, you start with some random numbers, and then you explore, exploit, take an action, and then maybe because you took an action, the environment gives back the next state and the reward number. Take that reward number. Okay, that's R here. You get the next state also. That's S prime here. Okay, and then you use the existing Q table. Okay, look at that existing Q table at that new state and look at which action is maximizing the Q value. Take that as a number here, and so now you have these two terms evaluated, and so you're going to adjust the original Q value at the current state in action with this adjustment. Okay, this extra term here. So you take the old value, okay, and multiply it with 1 minus alpha, and take this new update and multiply it with alpha. Okay, alpha is a number like 0.5 or something. And so that's written in a slightly different way here because this bracket, the thing inside the big bracket is called temporal difference error. Okay, and so that it relates to there's a whole family of temporal difference based algorithms, and Q-learning is one of them. So that's why it's written this way. But basically, this error is basically what you kind of add on or change the previous value from. Okay, so you have a previous value, this delta or whatever, some new number. Add to that, and so that's your new estimate at that state and action value. That's your Q-learning update step. Yeah, so I guess the full version is shown here. So the equation that we saw previously is exactly this in this update step here. Okay, and Q-learning itself, with this tabular view, we know that with some extra assumptions, kind of it converges in the sense that if you just do this explore exploit and keep updating like this, eventually you will get to the right Q star eventually. So this is actually I guess a consistency result informally speaking. Whereas if you remember with multi-on bandits, we had we didn't talk about much theoretical background there, but those multi-on bandit algorithms like UCB1 or Thompson sampling, they do satisfy something like this, the last claim that we're making here, but they also satisfy something called finite time bounds. So at given capital T, you can say that the regret is upper bounded by some term, for example. So you can actually get something like that even with Q-learning, but that just becomes more complicated. Okay. So what we want to switch over to now is that, okay, we know Q-learning, it works as long as you can maintain a table. So as long as if your problem is really small and you just want some software to figure out what to do in each state if in your environment, if your environment or a problem is really small, you can just apply Q-learning. That's a big very good hammer to use immediately if you don't need, if there are not too many states and not too many actions, I guess. But the moment you need scale, which is the moment you get into more interesting problems like self-driving or even playing games and stuff, it becomes harder. Okay, so for example, if you look at the left-hand side and the right-hand side, these two are just views of the same environment. In the left-hand side, somehow you're able to encode your position, for example, as an XY coordinate. So you're, for example, at this green dot, and you need to get to this door here. If you're just looking at XY coordinates, maybe this is the number of states is not too many, and you can just move forward, backward. You can figure out, okay, if you can measure yourself in this way. But if you have a view, so you as in like this green dot here, the agent, if they don't have this view of like their XY coordinate, absolute XY coordinate, but just look at this screen, okay, maybe the camera feed is the only input for them, then they will not be able to, and also just the XY coordinate, but you don't know the full you don't know how the grid is laid out. Okay, if you know everything, then that's a MDP style problem. planning problem. So if it's laid out like this, then your slight movement may change the camera feed. So you have to do something more, right? So you can't take each frame as a state, because then there are too many states. Okay, so slight change, or if you change a view, then there's going to be every such frame or an image. It cannot be a state by itself. Okay. So to fix that, that hey, we can have millions of states or even uncountable number of states. We'll try to adjust that, fix that by expanding Q-learning to take into account that there could be too many states. We'll still keep the number of actions finite, as in like a few, like 10 or 20 or whatever. There are algorithms which are designed for both infinite states and infinite actions. So actions can also be continuous. So in fact, self-driving, think of self-driving example. If you're steering, it's not like you'll only do like 10 different steer positions, for example, steer actions, right? There could be there could be a real number, okay, of the amount of steering you're doing, or amount of acceleration, or amount of braking you're doing, right? So but there are algorithms for that. For us, for now, we're just going to focus on states being too many. Okay, so what we're going to do is use a deep network or any function class, not just deep network, but any function to represent the value function, which is what we'll focus for Q-learning. But it can any function can represent a policy, a model, and so on, right? The few quantities that we saw from last time. But we'll focus on value function. So but once you say, instead of a table view that we saw with Q-learning, instead of table, you'll say, hey, there's a function. Then the function will have parameters. So you want to then optimize the function's parameters rather than doing a tabular update that we saw in the previous class or earlier today, right? So we want to optimize this network or function end to end, in the sense that some sort of a gradient descent type of procedure. Every time you interact, think of an ideal situation, right? I'm interacting, I get some reward next state, and then again I take some action, I get some reward next state, and so on. So maybe after every interaction, I should be able to, for example, do a gradient update and update my value function, or basically the function parameters, right? That's doable, and it seems similar to what you do with supervised learning, and that's what we'll try to achieve. Okay, so we want to optimize this underlying function class, whether it's a neural network or something else, its parameters, end to end, okay, based on just the reward signal. Okay? And so the optimization can be incremental. So after every update, or maybe after every 10 updates, I'll update the parameters. Okay. So I guess the gist is that instead of storing this table of number of states times number of actions in a table, we want to find a scalable way to capture this Q function. And so we'll say, hey, this Q function is represented by a function approximator. Okay, that's the word we use. It's an approximation for the original or true Q function, because, for example, if you use a function class like a linear function class, the true Q star, may not belong to linear function class, okay? Or the true Q star may not belong to the set of functions that are representable by your neural network architecture. Okay, so that's why it's an approximation word being used there. So we'll add tack on extra parameters for this Q function. So the left-hand side is a function approximator. So it's a function which takes two inputs and has also parameters inside, which produces a number, the Q value, which is as close to the true, hopefully, after learning, for example, will be as close to Q star of S, n. Okay, so there are two views actually, and these two figures blocks are just showing that you can either think of the Q of S, as the state action value function as take two inputs and produce one number. Okay, or actually, informally it also means, doesn't also mean, but informally you can also think of just taking a state as an input and producing one number for all the actions that are possible. Okay, so let's say there are 10 joystick actions or 18 joystick actions, then you can just produce 80 numbers directly. Okay, so the API is slightly different. Okay, it's just so think of the right hand side as like a wrapper around the left hand side. So it's just iterating over every action and tell me what the Q value is, and just producing that bunch of Q values. Okay. The reason I introduced that here is because you'll see that in DQN version. Okay. So these functions themselves can be anything. So function with parameter W can be a linear function, could be a decision tree, could be neural network, could be a collection of basis functions. Okay, or it could be also be it may not have a parameter. It could be just nearest neighbor model. Okay. Yeah. So let's see. Let's actually work through with some simple examples of how this approximation influences a few things, in particular learning. So you have this Q. So let's look at for a given policy, right? So Q pi of S comma A is for a given policy, a Q value for that policy. If we approximate it with a function, let's call it Q hat, which has parameters W, then what we can say is that there's going to be a difference between these two. So let's say, if you knew the Q values for a given policy, right? For a given policy, you can always compute Q of S comma A by Q pi of S comma A by just solving the Bellman expectation equation, for example. Right? So if you want to approximate this Q pi of S comma A, then what you do, you have this reference numbers for every state and action, that minus this Q hat of S comma A with W. You take the squared loss, some sort of squared loss, and you want to minimize with respect to W. Okay, so basically what I'm trying to set up is some sort of a loss function now, because we haven't seen an explicit loss function before in Q learning, or even in the last lecture. We were just talking about, hey, there's a value function, it has recursion, it has optimality and expectation equations, and therefore let's massage it so that we can directly get to Q star, right? Now we're gonna have to do, now we have introduced a function approximator, so we need to know how good the approximation is, and that's how we need to tune the W's, the parameters of this function approximator, right? So we'll have to have some sense of a loss function here. So we're not introducing a measure so that we can take a gradient with respect to it and update. Okay. So if somebody tells you what the Q pi of S comma A is, so for a given policy, what the Q values are, and you want to say, hey, I want to approximate this function with a parametric function with parameter W, then you can just say, hey, I can just minimize some sort of square loss, and then expectation with respect to expectation with respect to all the possible states that can happen, all the possible actions that can result based on pi. And so expectation with respect to pi just means, according to that derived distribution. Okay, so remember the Markov reward process, right? So that's what this is. So that's the loss function, and then you can just take a gradient descent. You can just do gradient descent with respect to that. Okay, so if you look at this expression here, then yeah, so if you take the negative 1/2 the gradient of J with respect to W, then it's something A minus B the whole square, right? So that's the term here, and then you also have the gradient of Q hat, which is still a function of W with respect to W, right? So what's happening is basically you just get a term because of the squared form, and then you get the gradient with respect to Q. We dropped the expectation, but you can always add an expectation here. Okay, so, and then you may say, hey, how does expectation and gradient kind of you can interchange? That's a nuanced topic, and so we'll kind of ignore that. Okay, so basically, our gradient update for the parameters of the function would be some difference between the target and your function prediction, some learning rate alpha times the gradient of your function with respect to W. Gradient of the function, not the loss. The loss is already, we are assuming squared loss. So this is the general expression. Okay, so let's actually think of a special case. Okay, so I'm just going to motivate a special case which will give you a sense of how the tabular view is related to general function approximation. Okay, so let's say we represent the state and action by a feature vector, in the sense that if you know state and action, from there first I want to construct a feature vector. Okay, and then I'm going to say the Q function is a linear transformation of this feature vector. Okay, so x of S comma A is just some features of state and action. So for example, if the state itself is a vector and action itself is a vector or some it's a categorical value, then you can say, hey, I have a vector and I have a categorical value. I can just concatenate them and call that the bigger thing as a feature vector, for example, right? So let's say x of S comma A is a feature vector. Then let's assume, and this is just again we are just doing an illustration. So let's assume that Q hat, I'm going to assume a function class which is a linear function class. So once I get the feature engineered feature vector, then x transpose W is my predictor for what the Q value is. Okay, so now I just need to update what the W's are, so that I just need to figure out the best W so that this approximates the Q star, right? Or any target Q. Okay, so Q hat is equal to inner product like this, which is the sum over, let's say there are n features here, then it's the sum over j is equal to 1 to n of the jth coordinate times wj. Okay, now this actually, if you think of the Q table, right? If you have a Q table, then the Q table will have numbers in the cells. Those numbers can be thought of as W's themselves. Okay, in the sense that you can think of in the Q table for a state and an action, there's a W corresponding to it. Your feature vector for a particular state and action can be a one-hot encoded vector, which will say, hey, you're in this state, you're in this action, in a really long vector, which is state times action length long. And then you can then this approximator just becomes the same as your tabular view. I don't know if you guys followed what I said. The tabular view is just a special case of linear expression like this, where the W's are just going to be the entries of the table. Okay, if you think of the feature vector to be an indicator of being in that state and action, like and all zeros everywhere else. So the feature vector length is state times action. Okay, instead of n here, so it's the state times action. So that times the numbers. If you want to pick the particular cell, then you just multiply in a product. Then you just get the cell number, right? So that will be W, appropriate W. Okay. Yeah. So let's say if but in general, let's say there's some feature vector and there is a particular function class that you're assuming. Then the gradient of Q hat with respect to W for at least this one is just X itself, right? So it's just a linear function. So if you take the gradient with respect to W is a vector, you'll get another vector, which is X itself. Okay, we have seen this a couple of times before. So if that is the case, then if you look at the previous expression, then the gradient of then the update on W, the parameters, okay, W new is equal to W old plus alpha times this difference times we had a gradient thing here that is equal to X, so we just put X here. Okay, so I'm just trying to derive the full expression for how to get the best function approximator if you know the reference, okay, if you know the target. But you'll see that in Q learning or in general reinforcement learning, we don't know the target. Okay, so we have to kind of switch out the target to something else, and that's what Q learning did actually. Okay, so let's look at the so basically, if this is the update for this type of a function approximator, that's fine. So this is a worked out example. There's an illustrative example of how you would approximate any function, any reference function. Now we'll come back to try to pattern match with the Q learning update and try to get a sense of what is the loss function for us for Q learning. Okay, when we do function approximation for Q learning. So far it's just any reference function. If you want to have a squared loss and approximate it, then this is how you do it. So Q learning update rule is this, right? So it's just the alpha times the temporal difference error is left hand side, and actually this is the update rule. So this is the new, this is the old stuff, and then the new information like reward and next state, right? So if you have this, we know that if actually things converge, right? So if the new one should be, if you remember what is convergence, right? So your numbers don't change. Okay, one I guess a very informal way of saying this, the numbers don't change. So this old should be the same as new, right? So it's essentially saying that if old is the same as new, then this term, error term, is not going to change, is not changing the old part. So which essentially means that the error term should itself be equal to 0. So I just added an expectation because all these are, there's randomness here. So there's a R is a random variable and S is a random variable and so on. So at optimality, basically this temporal difference error should be 0. Okay, so that gives us a motivation for how to define the square loss. Okay, so remember square loss, we had to have a reference. So what we can do is we can minimize the empirical error. We can minimize the error between these first two terms, okay, which is I guess some approximate reference now, and the third term, which is now our function approximator. So in the sense, we can plug in function approximator both sides. Okay, so we can say, hey, this is my some sort of a reference or a target variable y, and this on the on the last term left is the function that's trying to approximate this target. Okay, so but okay, so there's a w in both these expressions, both terms here. So this q function has a w parameter, this q function also has a w parameter, and if you just try to minimize the difference between these two over my data, then it's going to be a problematic, and we'll see how to fix that. Okay. Any questions here? Are everybody lost, or any questions? Question in chat. Okay, so the reason why, so this is all again hand wavy in the sense that it's informal. What we're trying to do is just say that, hey, what would happen? Like, how would I define some sort of a loss score? Right. So we need a loss score so that we can update the parameters of our approximating function. So we're going to get a loss score by trying to replace this thing in the blue with that r plus gamma max of q term that you saw. Okay, so that's all we are trying to do. Okay, so we're going to do that with the algorithm that we'll see pretty much in the the second part. So far what we've done is just motivate function approximation. Okay, we'll kind of finish up motivating function approximation in the next couple of slides, and then we'll come back to that squared error term, squared error objective function in a second. Okay, so let me come back to example. So this function approximation idea has been there for a long time, but the success in I guess 2013, about 9 years ago, on the suite of Atari games, 2D games, was kind of an important milestone for RL algorithms to be able to work on non-trivial as in non-toy settings. Okay, so in this case, these 2D games. So this is just an illustration of the games themselves. But we'll see that the algorithm actually was just a function approximation with Q learning with some couple of extra ideas. Okay. So there are some issues with function approximation, but let me briefly point them out. So there can be potentially a nonlinear optimization with respect to the parameters of the function. For example, if you use a neural network, then clearly all the neural network issues of, hey, how do we deal with gradients, vanishing gradients problem, unable to pass the gradients through and get to a good solution, all that stuff comes back. We can optimize incrementally or in batch. Batch is a version what we've been seeing with regular supervised learning. But here, the nature of the problem is generally incremental. Like every time step, there's a response back with a reward in the next state. And there's also issues with like naive optimization in the sense that if you just do gradient descent, in general, there could be an issue when you think, in contrast to supervised learning. Okay, in supervised learning, data is IID. Here, the data is not IID. Okay, so remember, you are taking action in a certain state. The next state depends on what action you took in a particular state. Okay, so that way, the data is not, exactly. Data is not IID. Okay, and so that can cause a lot of issues with optimization. Okay, so if you think of trying to use all the supervised learning machinery by easily, as long as you could define that loss function that we just saw a little bit earlier, that's not enough. Okay, and so these are the issues, IID, and then because of the max operation, and if you saw, there's a max operation here. So a slight change in the max can change this number quite a bit, right? So if A is not the max, but some other A prime is the max, then the number can jump, quite differently. Okay. So anyway, so those are some aspects, and so we'll see how they're fixed in the in the example DQN algorithm. Any questions here? Okay, so what we'll start with is where we left off is that we motivated that there is a need for function approximation, and we kind of worked through an illustration of how that would look like in terms of defining a loss function and defining parameters and potentially doing gradient descent on them. let's look at DQN and what function approximator it uses and how does it solve this. How does it work on these games that we saw in the previous slide? Okay. So DQN is an example algorithm in the deep reinforcement learning subfield. It basically brings the success of perception, how successful we have been in perception problems, supervised learning problems, to bring that machinery as function approximators in the RL setting. Okay, so we look at two RL agents in general, so which loosely I guess belong to the deep reinforcement learning bucket of techniques. DQN from 2013 and AlphaGo from 2016. Actually, there are other variants, but we'll just look at two canonical ones. And we will highlight some extra things, some new ideas that were kind of needed to make them succeed in the domains. Okay, and in fact, the problems that they solve, at least DQN, you'll see that it is actually conforms to our idea of a reinforcement learning setting. AlphaGo is not exactly a reinforcement learning setting. It's just a game setting where nothing is stochastic. For example, if you move a pawn from A to B, then it just goes there, right? So there's no stochasticity there, but still you can use RL as an approach there. Okay. So why deep representations? This motivation is not needed given our exposure to convolutional neural networks earlier in this course, but just kind of brief recap. I mean, if you recall, around 2010-11, there was a certain performance number in terms of accuracy that folks were able to reach in terms of this 1000 class classification problem, ImageNet problem, and then there's a sudden jump to by about 10 absolute units to 84% accuracy for this problem, and this jump was due to a deep neural network, right, AlexNet. Also, just note that this is a like top 5 error, not the usual binary. Sorry, it's not the usual accuracy function. It's like that accuracy in the top 5. But so that's what kind of has led to success, that you're able to really do well in supervised learning problems, right? And so earlier, instead of doing feature engineering and then a lot of feature engineering and then do one of the methods like SVM, here you're just directly inputting the raw data, raw measurements, and then hopefully there's some features that are automatically picked up by convolutional layers in this case, and then eventually that can lead you to classifying better. Okay. So anyway, so that's the motivation, and CNNs as a function approximator, they can capture nice properties about images. Okay, so the reason why I'm mentioning this is because we'll use DQN in the game playing setting, and in the game playing setting, we are going to actually get an image, okay, as an input. Okay, so clearly, we know what a conv layer does. There's local connections with weight sharing filters, basically shared weights. You apply the same filter everywhere, and you also do pooling so that if an image is somewhere else, sorry, if a particular feature is important in some top right or top left, it still kind of is coarsened out and still present. Okay, so there are some ideas which kind of help CNNs, at least for image data. Now, what we want to focus on is how DQN plays Atari games. So Atari learning suite, or sorry, the Atari games environment has a suite of like 48 or 50 games. And how does it conform to an RL setting? It's basically that you have, think of this brain as an agent. Okay, so for now, it could be a human, it could be, and in our case, we want to create software. The agent takes an action from the uses the joystick. That action, signal goes into this Atari game, I guess, game box. And then that action is also displayed as like what happens there, and you also get back a reward for that action that you took. Maybe you shot down some enemy and so on, and then what you observe is just the screen, right? You as a human will observe the screen, and so we wanted to mimic that. So even if we replace this brain with a human agent, we want to kind of only give visual feedback. Okay, so we get a score on the screen frame itself. Okay. Rules of the game are initially unknown, so think of, for the first time you're playing, you just don't know what leads to what high scores, but you'll play again and again and again, and hopefully you'll figure out, hey, if I do this or that action, I'm actually getting a higher score, and then you'll survive and so on. Right? So you're directly learning with interactive gameplay, and that's exactly the reinforcement learning setting, because you're getting reinforced by your trial and error choices, which is exactly exploration exploitation. Okay. So DQN basically picks up the Q learning, I guess, idea from before, and adds a few more ideas, including function approximation, so that it can actually work for these non-trivial settings, okay, environments. In particular, it uses a CNN as an approximator, and it does also a couple of things, as we saw when we're trying to motivate the squared loss. There was this W present in both the max of the function approximation as well as the third term. So there is some idea called freezing the target. So we'll see the idea of freezing of targets in a second. There's also an idea of how to do batch optimization. Okay, so we're going to rely on batch optimization rather than getting a new reward and a new state and then immediately doing gradient update. Okay, we're not going to do that. We'll try to batch data and then do an update. Okay. So the network itself is pretty straightforward. Actually, it's not really a deep network in 2022 terms, because you can see that it's actually 2 con layers and 2 hidden linear layers as shown in this figure. So there's a few additional minor details. First is that the Q function is approximated by CNN. The input itself is actually a stack of 4 images. Okay, instead of 1 image, it's 4 images. Okay, so 484 cross 84 is the size of the input tensor, and there are some specifications like 8 cross 8 filters, 4 cross 4 filters. Those are something that we've seen before, and then a number of hidden units leading to the output layer. The output layer produces 18 scores. So 18 scores. This corresponds to the expression I showed you, right? So 18 scores because you get a state. So think of the state as these 4 images. Given the state, you're just producing Q value, your estimate of Q value for each of the 18 joystick movements you can do. Okay, so for each of the joystick movement, there is some value of doing that, and so you can figure out which one to do by just taking a argmax of them. Okay, so whichever is more valuable to do in this particular state is the one you ideally want to do. Okay, I ideally want to play. Of course, you don't want to directly play that. Remember, there's an explore exploit step. So with some probability you will do that. With some other probability you'll pick a random joystick action. Okay. And the reward is the change in score for that step. So you get the screen. So you look at a particular area where score is being displayed. So every time the score, from every time you get a new set of these frames, you see whether the score changes or not, and whether you the game ended or not. Okay, so that's the reward that you can see. So what remains to be said is how do we tune the parameters? In this case, how do we tune the filter weights or the weights of these 2 fully connected layers, right? So those are the parameters that we need to change. Okay, and we want to rely on Q learning update or something that looks like that. Okay. So we're gonna see that batch learning process in this slide. In particular, what we'll do is we're going to somehow have to get a hold of a definition of batch, right? So for that, there's a notion of experience replay idea. We'll talk about that, just now. And there's also this notion of a fixed Q target. Okay, so those are the 2 new ideas, in addition to modifying the Q learning for function approximation to get this into a batch setting and also deal with instability issues that I briefly mentioned earlier. Okay, so at least the easy part. So the easy part is very similar to easy part is going to be picking an action, right? Picking an action is epsilon greedy, very similar to Q learning. So you pick a action according to the epsilon greedy policy from the current Q function. Okay, so your current state, you can evaluate 18 numbers. You can either take the argmax of them, 18 numbers, or you take a random action. Okay. Then what we do is, now we want to focus on the update step. Okay, what we do is actually take okay, we are in some state, we took certain action, we got some reward, and we got some next state. Okay, so that 4 tuple, we're just going to put that in a store. Okay, think of it as like a cache or some sort of a store database. So we're just going to put this 4 tuple in a replay memory, and that's also called the experience replay memory, script B. And then what we're going to do is sample a random mini batch of transitions. Okay, so random mini batch of these 4 tuples from D. Okay, so we're going to sample maybe 10 or 100 of these. Okay, so remember, we keep adding such experiences, such 4 tuples in this database or memory D, and then we sample a few. So the sampled ones need not be related to the latest observation you made. Okay, so in fact, the sampled one could most likely be some other unrelated state action reward and next state pair. Okay, tuple. Then what we'll do is now we're going to form the target, as in the y variable. If you think of regression, we need to first define y, and then we'll say f theta, and we'll kind of adjust theta so that it predicts y, right? So we're going to focus on the target. So the target for that regression, some sort of square loss objective that we want, we're gonna compute the target using some parameters w, which we call w minus. Okay, and that's kind of related to the idea of fixed q targets. Let me show you what I mean. So you sample a mini batch. Now let's say you have w minus as some parameters. Then you first estimate these two terms. Okay, the terms I'm showing you here is r and I don't know, yeah, sorry, r and gamma times max of a prime of q. Okay, so this r plus gamma max is the same as before, same as q learning, except the q function is being evaluated with respect to parameters which are some old parameters. Okay, old parameters just means, okay, let's say 1 minute ago or 2 minutes ago or 2 iterations ago, whatever was the weights you had, those are the weights that are frozen, in the sense that they're kind of being fixed to evaluate the reference or the target. Okay, so you compute this becomes your kind of y. Okay, so y, and then y as in, if you think of supervised learning, there's a y, right? So if you think of regression, for example, so you can compute this target, and then you have y minus f of some input and parameters, right? So you want to optimize the parameters such that the f function produces something close to y, right? That's the square loss here. And what is the data set that's used? So you just need to use the random mini batch that you sample from your memory. Okay, so the experience replay part is all about this, putting all your new experience into memory and only sampling a random mini batch from there. Okay, that's the replay part, experience replay part. And then fixed Q targets is because you want to decouple these weights from these weights. Otherwise, it becomes a very messy optimization over the weights. In this version, it actually becomes very similar to supervised learning, right? So these two, this r plus gamma something, there's some number. Okay, so you produce one number, and you can produce one number per tuple. Okay, and then you have a deep network. Okay, so you're literally just doing regression here. You have a number, and you want to kind of approximate that number by a deep neural network, and so that's exactly regression using neural, in this case, convolution neural network, right? So and then you can use any Adam optimizer and things like that you've seen in your assignments. So that's DQN algorithm. Any questions here? Deep Q network. Yeah. Okay. So that's again, instead of looking at the equation, let's look at the block diagram view. So what's happening is the one in purple is the environment. The API is still the same. You get a state, given in that state, you want to figure out what action to take. Okay, you get a state as well as you get a reward, but reward stuff is being stored into replay memory. So state information, action, reward, and next state is being stored in replay memory. Once I get a state, I just have to say, hey, at this state, let me evaluate all my Q, given my Q function, evaluate what all the values of different actions are. Take the best action, that's argmax here. Okay, so you can take the best action. If you're still learning, you have to do epsilon greedy here, not always the best action. Okay, so that's the interaction between your policy, so between your Q function, which is represented using a network, and the environment, right? So this interaction is clear, and then we're storing data. Now what we need to do is update this Q network parameters. Okay, so this Q network parameters. For that, what we essentially have is a reference Q networks, okay, a clone of this network with slightly different parameters. Okay, so these parameters here on the left side are called theta. We need to gradient descent on theta, okay, using square law. The parameters in the right block, they're called theta minus or theta minus, and they are just some older snapshots of this theta value. Okay, from maybe 10 iterations ago or 20 iterations ago or something like that. Okay, And then given you draw a sample from the draw a mini batch from the replay memory SA, SR, S prime, R prime. This need not be the same as this guy. Okay, this could be some maybe 10 interactions ago, some state action, next state reward that happened. What you can do is given SA, that's the input to your function. Your function has to predict the reference, which is given by the target plus the immediate reward. Okay, so max of A prime of Q at A prime and theta minus plus R, that would be the reference. And your Q function has to approximate that. And if the difference between them would be the gradient, and the gradient is with respect to theta, and that will be used to update the parameters theta. Okay, so that's what's happening in this diagram. Is the diagram view at least better? Okay. Okay, let me kind of at least show some what happened with that 2013 effort, right? 2013 to 2015. So here we're just seeing the performance of the DQN approach versus a linear function approximation approach. So you can always, instead of a deep network, why not just use a linear function approximation, right? So you can do some feature engineering and then just say, okay, it's a linear transformation of that is my Q function. Okay, so is my Q function. So the gray and the blue bars represent that, and then at some, these x-axis shows the different gains. So they're ordered such that higher performance is on the left and lower performance on the right. And then at some level, you can see on the left side would be better performance than humans. Okay, the average human, and then on the right side is worse performance than the average human. Okay, and so you can see how different approaches, how much better and worse than each other, and with respect to human level is being achieved here. So, for example, for some games like video pinball, it's like 2,500% better, and then 330% better than humans, okay, than a human level player. So this is the although there are all these different games, what we're doing is actually the same neural network, architecture, not the same neural network weights, same architecture, same 8 cross 8 filters, 4 cross 4 filters that we saw, same CNN basically, same hyperparameters. All it's doing is they get plugged into a different game and they keep doing trial and error, and they will, over a lot of iterations, figure out what's the best thing to do. Okay. So the question is, did the extensions help, right? So what are the extensions? One is this freezing of Q targets, Q, if you theta minus or W minus that we saw before. Second extension is the use of a replay buffer. Okay. If you don't do those two, then you have the original Q learning with the function approximation. Okay. So so if you look at the, let's start from the rightmost side. So no replay Q learning is producing some performance on a few of these games, like 5 of these games listed here. Okay, and if you now add, instead of don't add replay buffer, but just add this reference Q minus or theta minus or W minus parameter, such that your targets are well defined. This stabilizes the loss function basically. So you can see there's an improvement, right? So you can see that from 3 units you got to 10 units. Now, if instead of doing fixed Q from Q learning, if you just add replay to Q learning and don't do fixed Q, then you're going from 3 to 240. Okay, so there's also a bump there. Now, if you do both replay buffer and a fixed Q idea or target freezing idea, then you're going from 3 to 300. Okay, so that's why. So this is a study to show that whatever you're doing is meaningfully adding to performance improvement, right? So you have to try out, since there are 2 ideas, you have to try the presence and absence of one or the other, and then presence of both being the first column here. How does it improve performance? Yeah, so this is an older result from 2015. So just trying to show how much progress we've made since 2015. So around that time, to train on one game was, back in 2013 and 14 was 14 days. Okay, 14 days of compute on a GPU. to be able to train. The neural network is not complicated, right? It's just two con layers and two polygon layers. To that much effort was needed. Instead of that, for example, Google proposed something in 2015 to speed that up from 14 days to 6 hours per game. Okay, so and that required trying to do some parallelization ideas. So basically, do 100 actors just mean 100 times, like 100 parallel creations of environments, 100 parallel games of same game, 100 times being played simultaneously, and somehow aggregating the experience together and somehow doing grain descent on all these parallel experiences that you're getting. Okay, so there had some, looks like complicated architecture compared to our previous figure, but it got some speed up and some speed up at the expense of more compute. Okay, this was in 2015, but in 2022 you can actually train such a network maybe in Google Colab, for example, right? So we've come a long way from there. Okay, any questions about DQN? This is the algorithm that you'll see in the assignment. Yeah, let me just briefly show the code, and then we'll take a break. Yeah, so as you can see here, so it's not implemented the same way. So DQN for Atari games had two con layers and then two fully connected layers. Here, the neural network has three fully connected layers because it's producing two scores instead of the 18 joystick numbers. Okay, two scores for two actions you can take to balance the card pole left or right. Okay, you can go left or right so that you can balance the card pole here, and you can see the forward step defined as this, and then remember Q-learning you have to do a little bit of exploration. So with some probability you will you'll flip a coin, and if the coin is less than epsilon, you'll take a random integer, 0 or 1. 0 represents go left, or 1 represents go right, basically, for the cards below the pole, or you can take the argmax. Okay, so that's the sampling action. So this is the network, and then the training part is very similar to how you do training. So here we are just using a slightly different loss instead of square loss. It's called smooth L1 loss, but loss function is slightly different. But you can change it to, for example, square loss if you want, and then the usual 0 degradients, do a 0 degradients, and then do a backward step and backward computation, and then step optimizer update step. Okay. Okay, so let's actually take a break for 10 minutes. Resume at 4:45, and we'll talk about AlphaGo. Yeah, before I jump to the second case study, so I want to quickly show you. We've seen this before, and there are many other examples. Okay, I think in the first lecture I might have shown you some other examples with Breakout and things like that. Breakout is an Atari game that I think we saw in the first lecture, but for this one, right? Just wanted to kind of close the loop because we saw this before in two lectures ago or last lecture, and this one actually is just using Q-learning, so it's not really using deep Q-learning. They're just somehow creating states, actions, discount, the step size, and then just keeping an array like this, and then able to initialize as random numbers, and then select and carry out an action, and then do a Q-learning update. So this is basically the algorithm behind learning to do well on Flappy Bird, right? So do well over here, right? And in fact, they tell you what at least this page, which is linked on the course page, tells you what the state space is, what the states are. States is the distance from the pipe, distance from the next pair of pipes, and whether you're alive or dead, for example. And then actions are going to be click or do nothing. So two-dimensional actions. Sorry, two actions that you can take: click or don't click. And then rewards are if you're still alive +1, and if you're dead like -1000. So based on the action. So just based on this, interacting with the simulator here, are able to learn a policy. Okay, so you should check it out. Although I believe the code base is in is in JavaScript, but you can check. You can get the Python based version as well. Okay. Anyway, so with that, let me actually come back to our material. So what we've done so far before the break is look at function approximation and then look at DQN. DQN as example is actually just a case study for how that particular architecture looks like. The takeaway is not so much about hey, DQN, this is what we need to memorize in terms of the algorithmic structure. It's more about hey, these are the tricks that people have figured out to kind of set up a neural network based RL agent. That's how it'll learn. Not just DQN, there are actually many variations of Q function based approaches. Double DQN, double dueling DQN, and so on. There are many names. And similarly, there are other approaches which focus on directly optimizing for what is called a policy function. So a policy itself can also be approximated by neural network, because given a state you're taking an action, that mapping can be a neural network, and then you can directly optimize for the weights of that policy function. Right? So there are many approaches like that. And so the objective for DQN, as well as what we'll see now, is just so that is just an example exposure to some details about these two example architectures. Okay, it's not really about generalizable patterns too much. I mean, there are some generalizable ideas, but it's more about exposure of a deep dive into a case. Okay. So with that, let me mention let's get started with the next example, AlphaGo for the game of Go. So so the reason why this case, we're looking at this example is because it's not exactly a pure RL setting. So Flappy Bird or DQN, there was an environment, basically a game, and you just had to control the joystick, right? So you had like 10 actions or 2 actions, and then you just had to, based on your joystick movement, some score would be increasing or decreasing, and that's about it, right? So this one is actually slightly different. This is actually, if you think of the game itself is there's no stochasticity, no randomness, and there's no rewards also, in the sense that either you win the game or lose the game at the end. In between, like it's just state of the system, state of the board. Okay. So in 2016, as I mentioned a couple of times earlier, a team, Google DeepMind, was able to challenge a top-ranked player and defeat the human player 4-1 in that 5-game series, right? And so we look at at least get a sense of the solution that kind of powered that outcome. Since then, the AlphaGo, there are many variations now, Alpha 0 and so on, which are much better than human players. Okay, so very similar to how computer-based chess game engines, chess game engines are way better than humans. Okay, so we can't compete with them, but at that time, it was a breakthrough. So what is the game of Go? Very brief mention about them, about the game. So it's a really old game, but has a lot of states in the sense that the board states how the stones are laid out on the board. Okay, so very similar to chess, if you've seen chess or other board games. So there are 2 players, and both players place stones, in this case white and black stones, at these intersections, crisscrossing intersections, and then based on how you place your stones, you can gain territory and actually win the game. Okay, so you can see, for example, if you surround the black stones with your white stones, then you have captured that region. And if you and maybe if you have a contiguous set of white stones, you have kind of conquered some territory, basically. Okay, so but the number of states is too many. Okay, so this combination is what is messes up in these games, in the sense that the computer has to naively evaluate. Okay, if the computer is playing against a human, it has to naively evaluate what all can happen in the future, and based on that, take a decision on what stone to place. Then there are too many situations to consider. Okay, so you can't linearly enumerate, hey, in this state, and this could happen, this is how human player will play, and so on. So it's kind of very hard to estimate like how to play against a human player. Okay, or play against any opponent. So if you step back from Go, actually, if you focus only on RL-based techniques, okay, RL-based techniques on other games. So if you look at this table, it turns out that it was just a game of Go where we were still like lagging behind, for example, the levels, the right levels, in the sense that was one of the only classic board games where AI agents were not the best. Okay, so in the sense that I'm only focusing on RL agents, not other solutions. For example, chess, there are other solutions that you're probably aware of, but you can see that this for the game of Go, the solutions at that point of time were actually kind of limited in the sense that, for example, Mogo could only play on a smaller board. So this game of Go board that you saw in the previous slide, the standard version is 19x19. On 9x9, there was some performance by a known technique called Mogo, which is RL based. Okay, these are all RL based techniques. So Go was not doing that well in terms of, like, we were not able to construct these agents which can do well in Go, and that's because of huge state space. The rules are pretty simple, very similar to, for example, chess or these other games. The rules are just to capture the opponent's stones or capture as much territory as possible. Okay, so those are the rules. So these are just superhuman. Just we can look at this slide deck or this reference, but level of play just means these levels are not comparable across games, right? So international master for chess, there's no equivalent for backgammon or something like that, right? So level of play just means how well this particular RL agents or RL programs are doing. Superhuman just means they can beat humans here. So here, although I'm saying grandmaster, so Go has levels, okay, very similar to chess, right? So I think Dan 9, and so there are a few names I actually don't know, but so within the Go leveling system, we were not able to compete with humans around till 2016. Okay, we as in like the software was not able to compete with humans. Yeah. Okay, so with that context of, we'll come back to Go in a few slides from now. But before that, what we're going to discuss is the casting the problem in agnostic to the particular game right now, but casting the problem as a search problem. Search problem because we know the board, we know the rules of the game, so we know a lot of information that is not typical in the for example, the Atari game setting. Atari game setting, you just have a neural network, and nobody tells you what the rules of the games are. You do trial and error, get the screen scores and so on. You learn. Okay, so rules of games are encoded in that simulator, that the game box itself. Okay? So you don't know a priori what the rules of the game are. Here, somebody can write down, hey, if try to put your stone such that if you get surrounded by other stones, you lose the territory and so on. So you can and if you place a stone, the next state is kind of clear. Like if you have a state which is a board state, and if you put a stone somewhere, and you know what the next state is, exactly the previous state plus the extra stone. So there's nothing complicated going on, right? But anyway, so the problem, the way we'll cast the problem is not as a reinforcement learning problem itself, but as a planning problem. Okay, in the sense that so if you think of sequential decision making problems, which are also a subset within decision making. So within decision making, sequential decision making, within sequential decision making, RL is one version of the problem where you don't know anything about the world or the environment you're interacting with. The second version, as I said, is for example, MDP. The second version is I would say planning problems. MDP is one of them. Another planning problem that we'll kind of introduce now is called forward search problem. Okay, forward search problem is a planning problem, very similar to the MDP problem. Okay, and here, planning problems, we know everything about the world. Like like in this case, like how to play the game of Go, we know. But the difference between MDP and the forward search problem is in MDP you're trying to find the policy, which very similar to RL, which tells you what to do in every state. Okay? In the forward search problem, we are not interested in figuring out what to do in every state. We just want to know in the current state what should I do. Okay, so it's a little bit the scope is different, and so forward search problem is about what action to take next. Okay, so we'll come back to this with an illustration in a second. For the game of Go, the forward search problem is how basically what action to take next is basically where to put my stone. So you have a like, for example, if you take given the current board state, if you put the stone somewhere, you're going to get a new position. So how good is that position basically? right? So in the game of Go, what is the reward function? The reward function is 0. Both players are placing stones on the board. There's no, they don't get any points till somebody wins. So let's say, at some terminal situation, time step t, let's say the black player wins, then then let's say the RT value is equal to 1, and if white player wins, the RT value is 0. If you have a policy, okay, if this is a game, so both players are playing, both players are following some policies, right? So what to do in each situation. So let's combine, let's just put them together, zip them up basically. Let's call that policy pi. Okay, it's just the moves of both players. Okay? If you given a pi, you can find what is the probability of what is the expected value of RT. Okay, what is the expected value of RT starting from a given position, given a policy, followed by the black player and followed by the white player. Okay, so this expectation is nothing but the probability that the black wins given starting state. Okay, under this policy. Okay, that is the value of being in that state. Okay, so we are trying to define a value function for this two-player game. We are saying you have the board state. What is the value of being in a state is under a policy. The policy says, hey, what all white player can do, white stone player can do, and what all the black player can do. You just take the, there could be many situations that can happen from the current state of them playing something, the other person playing something else, and so on. Given all that information, on average, what is RT value? Okay, so on average, maybe black wins 60% of the time. Then that is the value of being in a state. Okay, so you want to be in states where your probability of you winning is as high as possible, right? So and then if you can define value function, then the objective becomes a minimax problem, where the black player is trying to maximize this value and the white player is just doing the opposite. Okay. So this is a twist from Q learning, optimal Q values, where optimal Q values would be just max of your policy. Okay, so V pi and V star are defined this way. But let's come back to the forward search in general. Okay, so forward search, as I said, is about selecting the best action, and it's a planning problem, which means that we know what can happen if we take an action, if we take some other action, what would the board state be, and so on. So we know, in the sense that we know the rules, and so we have access to a a simulator basically, where we can say, hey, if I do this is the state. If I do something else, this is the state, and so on. Right? So we want to figure out the best action by looking ahead. So think of it this way, right? So if you are a player playing against an opponent, it's as if you can take a snapshot of what the current board state is, go back to your drawing board and see, hey, these all can happen. That's what you're looking ahead, what all can happen, and then let's you decide what to take now. Coming back to the real world and taking action. Yeah. You can't look every possible case, right? You can't, and that's the issue here. I mean, if you could, then yeah, everything is simple. Yeah. So how do you decide which ones to look at? We will. That's exactly the content for this next 40 minutes. Yeah, next hour, right? So how to look ahead, right? So that's what Monte Carlo tree search idea comes to the rescue. So how do you look ahead? So basically, forward search, in general, the core element is going to be, there's going to be a search tree where the current state is going to be the root, and then all possible things that can happen from the current state. Okay. And so to say what all possible things can happen, you also need to have an access to something which tells you what happens under every action, right? So you're in state ST, you took action 1 or action 2. If you take action 1, and maybe the opponent also takes some other action, then you get to some other state, and you can get to some other state where maybe some probability, maybe some other probability. So think of, and maybe after that you took some action, maybe you lost, and maybe you took some other action you won, or something like that. Okay, so all these can happen. This is just the full binary, not binary, but like whatever is the number of branching out factor that is, full expansion. That's the search tree. Okay. But at least this search tree is a little bit different from solving the MVP, because you're just focusing on although you're looking ahead, all you care about is what to do, whether to take action 1 or whether to take action 2, for example. Okay, so that's the only answer you want to report back. Okay. So how do we do? One approach is to actually, as you said, the search tree could have a huge branching factor, and we can't explore every path, reaching to some terminal state where either one person wins or the other person wins. So we will we will simulate, as in like sample some of these trajectories that can happen from now. Okay, so maybe although the branching factor, let's say, is like 10, then 10 to the power 10 times 10 times 10 times, there's going to be a huge explosion, right? Instead of that, we'll just sample some paths. Okay, so maybe I take some action. From this action, many other things are possible, but maybe I'll look at one path where I reach some state next, and I took some other action. I reached some state out of multiple states I could have reached, and so on, and then look at the termination. What happened? Did I win or not? Okay, so so we'll simulate episodes, and then later on we'll see we can apply model-free RL idea. Okay, what does a model-free RL idea mean? Later on, we'll try to use the Q-learning idea. Okay, so sorry, not Q-learning idea, but we'll use the value for value. We'll use the notion of a value function to value actions. Okay, because we have to take an action at this point. We are in current state. Let's say there are two actions to take. We need to value how good one action is versus the other. Okay, and that value has to be long-term value, right? The game can end like long time from now, for example. So you need that long-term value of taking an action now. So that naturally tells you that we need to pick up some model-free RL component like a value function. Okay? Model-free RL component like a value function. I'm using that word only to say that it's different from the value function. Directly is not talking about like a policy or a model, right? So it's a indirect object. Okay, you don't need to have an explicit transition function or reward function for that. Okay, that's all it means. Yeah. Okay, so let's actually focus on simulating episodes. So what do simulated episodes mean? I'm at a starting state, let's say ST. Okay, from there somehow I need to kind of keep accumulate experiences, some experiences. Okay, and this is all, by the way, not in the real game, but I have, since I know the rules, I can simulate. Okay? So I need to collect experiences. Let's say I collect capital K experiences. How do I do that? So I'm at the starting state. I can, I can use some default policy. Okay, so now that's another ingredient that's coming in the picture. I can just, for example, flip a coin and take an action, flip another coin, maybe take opponent's action on their behalf, keep flipping a coin, and then eventually get to some terminal state. Okay, that's also something that you could do. So you need to have a notion of some sort of default or a behavior policy that you're going to use. Okay, so that's how you'll simulate, right? Somebody has to tell what action happened, what the next state is. Next state given action is probably easy, but what action to take, somebody has to tell, and so we'll have to use some heuristic there. Okay. We'll look at applying model-free RL idea in a second. In fact, we'll look at simple Monte Carlo search, which actually is quite effective. Okay, which just relies on simulated episodes of experience and notion of a Q function, and then more efficient version of Monte Carlo search. Okay, so that's these two ideas actually take care of this explosion in the search tree that you mentioned. Okay. So what is simple Monte Carlo search? It's just a warm-up algorithm. I mean, Monte Carlo tree search is just an improvement of this. So this idea is actually also simple, or at least straightforward. The idea is you need a model of the environment, as in like you need something to say, hey, if I take this action, what will happen? And for the game of Go, it's very simple. If you take an action, literally the stone will be placed there. And in case you cover the territory, you'll get some. You'll be able to remove some stones, or if you're able to encircle some region, then the other person cannot put a stone in there or something like that. Okay, so those are some rules. And you also need a simulation policy or a behavior policy or a default policy. Okay, you need a policy. Then what you do is for each action that you have a choice to make, right? You can put a stone on the left side or the right side, or at some of the intersections. For each choice that you have, you say, hey, given the starting state and the choice, let me simulate what all can happen according to my policy, according to some policy, some default, like a random policy, for example. Here we're calling it a simulation policy according to the dynamics of the game and the policy part. Okay, so we kind of keep simulating what can happen. Okay, then as we saw with the model-free RL idea is basically, hey, why don't you estimate a Q function, right? So given the starting state and action A, the Q function is the long-term value of being in that state and taking that action. Is just out of the K simulations I did with these two starting points, what is the total return I got? Okay, GT is the same total return random variable. Okay, the return random variable, sorry. which is just and if you remember the game of Go, there's no return, there's no reward, any intermediate step. Basically, at the end of the game, you win or lose. And so if you are a black player, you win, then you get 1 point, for example. So take an average, okay? And that average, actually turns out to be the Q value. This kind of expected, right? That's actually just the Q value given the simulation policy, starting from the state and taking action A. Okay, that's known. Now what we'll do is just select the real action. So with this simulation, if you get these estimates, then we can just take the R max over any of these actions, and then given these estimated Q values, and then take that action. Okay. So of course, our estimates really depend on what behavior policy, the simulation policy is. If it's a very terrible policy, it may send us to taking a wrong action. But this is pretty much the idea of simple Monte Carlo search. So what is it fetching us? It's that the search tree is huge, and so you can't evaluate every possible outcome and then get a sense of which action to take now. Okay, and so instead of that, you're just picking up some particular trajectories in that search tree, okay? And then just based on them, you're trying to evaluate whether one action is better than the other. And to simulate beyond that action level, you need a simulation policy to kind of go through that trajectory, get that trajectory. Right. So in terms of, I guess, illustration, so you're in some current board position, like these black and white stones here, and then you can say, hey, if I take action like put the stone here versus here, I guess they're the same, but yeah, this is just showing board states. So think of the illustration actually, just board states will evolve at the end of the game. Maybe the black player won here in these two cases, and in these two cases the player did not win. Okay, so based on this, you can get a sense of what is the value of being in the state. Okay, but you can also, but this is just for illustration. You actually compute the Q value of being in a state and taking action. Okay, is that clear? Any questions? Okay, so that's simple Monte Carlo search, and in fact, it's a very straightforward idea, right? So since you cannot try out everything, you try some samples, and then based on some estimate the action to take now. Right? That itself is a first, I guess, a baseline technique for solving the forward search problem. Okay, even though your search tree could be really large. The next idea is to make this a little bit more efficient. That's called Monte Carlo tree search. So what it does is instead of so what we start doing is, instead of just simulating using the simulation policy, or I guess the default policy here, the name default and simulation policy are the same. Instead of directly always using the default policy next step onwards, we're gonna slowly start building what is called a tree policy. Okay, we're gonna slowly start building a tree policy. So always think in terms of this diagram here, okay, or the previous diagram. So all I'm trying to say is that all these, what do these policies do, right? So the simulation policy or default policy, all they let you choose one trajectory here. They'll pass you one trajectory. So what you're trying to do is slowly start building what is called a tree policy. Okay, what tree policy, again, it's a policy, so it'll let you choose how to go down this, any of this, how to go down the search tree. What we're going to do is try to build a tree policy in the sense that the tree policy is going to cover some part of the search tree. Okay, think of like a circle. Okay, there's a circle here, it expands and covers a little bit more states, expands a little bit, covers more states. So tree policy is something that will kind of keeps expanding a little bit, covers a little bit more of the states, more of the search tree nodes. Okay, but and so there's going to be a boundary after which I'm going to keep using the default or simulation policy. Before the boundary, I'm going to have this tree policy determine how to go down my path. So all I'm trying to say is that simple Monte Carlo search, after taking action, you kind of always use default policy or the simulation policy. In the Monte Carlo tree search case, you're gonna have a notion of a tree policy that you're gonna slowly construct as a expanding, and keep expanding from your root. Okay. So then, and both are policies, so they just let you decide where to go next. Okay. Whether to go left or right and so on. So let's say and so this illustration, let's start with the illustration first and then look at some equations, and there's no, they're not complicated. So you have a current, you start with the starting state, And then initially tree policy is going to be nothing. So you're just going to use the default policy and go through some trajectory, and maybe you won. Okay. And then you have a sense of, okay, the value of that state is, one victory out of one try. And then maybe and then what you do is try to now increase the region within which now you're going to be a little bit more intelligent. Instead of directly applying default policy, you're going to say, okay, I didn't try a particular action. So let's say there are 2 or 3 actions available. I didn't try one of these actions. Let me try that specific action and then do a default policy. So now you're now you're being a little bit more directed. Instead of using default policies action, you're using tree policies action. Then go down. Maybe you got a 0 reward. Then you say, hey, okay, for that action, starting from the state, I'm going to attribute a score of 0 out of 1. Okay. And the 2 tries, I still have 1 point for some, from the previous iteration. And then, okay, I tried this action. Maybe there's one more action which I've never tried. I've tried one action, but I've never tried another action. Maybe I should try that one now. Okay, now again, I'm not following the default policy in that immediate step. I'm using slightly different logic, right? So that's why it's called, it's called a tree policy. And then under that, I won out of 1 try. So I've got 1 out of 1 score here and 0 out of 1 score here. So this now looks like these 2 scores here, 1 out of 1 and 0 out of 1, look like multi-armed bandits estimates of 2 arms. Okay, so from the starting state, it looks like I have 2 arms. I tried 1 arm, I got a 0 score. I tried another arm, I got a score of 1. Okay. Now the question is whether I should exploit or explore, right? Should I, like you can see from this perspective, right? The 2 actions, I can either exploit or explore. So maybe you chose exploit, and so you continue with the more promising action that you took. But then you say, okay, from this action, I'm going to now start again, try to increase my tree policy area, okay, a little bit more. So again, I'm going to be not following default policy from this point onwards, but say, okay, I didn't try a specific action. Let me try that action. Maybe there are 2 actions available here. Let me try a specific action and see how that performs. Maybe that action actually led to 0 reward. Then I'm going to have a score of 0 out of 1 here, and backdrop, and give a score of 1 out of 2 here. Okay, so now the score also changed because remember I exploited, got some 0 score, so that's 1 out of 2. But I also now included, because I didn't follow the default policy here, I changed my idea, so change the way I pick an action. So so this part becomes part of now the tree policy. Okay, so what happens through this Monte Carlo tree search is that the tree search part is just saying that you're going to slowly start creating a region around, starting from the starting root, where you're not going to follow the default policy. You're going to be acting like a multi-armed bandit algorithm. Okay. In fact, the idea here is to use q-value functions and bonus. I think you've seen used to be 1. So basically q-value function plus bonus is what you do. So let me, yeah, and then since you in the next time again, you can, maybe you chose to exploit again, since you chose to exploit, but the actions here, only 1 action has been explored, the second action has to be explored, then that's a heuristic being followed here. And so you have to explore that action. Maybe you got 1 point, then 2/3 and so on. Okay. And for example, the next time, maybe instead of exploiting, maybe you'll explore, depends on the bonus term, for example. Okay. So you'll not, just because you got a 0 here, it's not like you'll stop exploring here. Okay. But once you get there, again, you will try to add 1 node. There will be 2 actions, let's say. Then from this node onwards, it's not like you'll do random simulation, or the default policy. You will pick 1 action, you'll pick the second action potentially, and so on. So there's a little bit more directed way of picking actions closer to the starting state. Okay, so that's a tree search idea. I'm saying this very informally via this diagram. If you look at Wikipedia page or other treatments, there's an explicit procedure of, hey, do this, do that, do this. It's not super important that we learn the exact procedure. The general idea counts. Okay, we just don't want to take into account that because in simple Monte Carlo research, the first simulation may go in certain direction. That doesn't inform where the next simulation should go. Okay, so there's no, it's like A/B testing. You just randomly simulate one trajectory, and then again randomly simulate another trajectory, randomly simulate some trajectory, and then take an estimate of which action is best. Okay, here now we're being a little bit adaptive. So the previous simulations influence where we go. Okay, that's a very, very important feature, because if previous simulations gave a higher score to this action compared to 0 this action, then I'm going to be more and more trying this side, okay, because I will be trying to exploit. Okay, if it was full exploration, then it's literally just randomly. It's going to be exactly Monte Carlo, the simple Monte Carlo search. Okay, so now to exploit and explore, that's where the bandit type of idea comes in. Okay, so what's written in the what I illustrated in the previous slide, there are explicit names for these steps. I'm only going to mention the step called evaluation step. There are like 4 steps here, but in Monte Carlo research, but I'm going to only mention one of them. Yeah, let me mention the Monte Carlo research, the evaluation step, and then the full algorithm again. So we have the model. We simulate K policies using using the current simulation policy, right? So we have a search tree containing the visitor states and actions, right? So for each state action pair in that search tree, we can attribute a Q value. Okay, so not just the Q value for the starting route and the 2 actions that you could take, but you can attribute Q values to any future states and actions that you can take as well. Okay, so you can get a Q value for them as well. Once you get these Q values, of course, you'll take the Q values related to the starting state only, and then take the argmax. Okay, so this is just trying to say how do you evaluate the Q values. This is just a formula for Q values. Let's not focus on that. So let me come back to the MDP, the Monte Carlo research, the overall procedure. Okay, so the difference with simple Monte Carlo search is, as I said, the simulation policy. The simulation policy improves in the sense that the default policy is being applied less and less later on, whereas the tree policy is being applied more and more. Okay, so the tree policy kind of you are more intelligent while choosing which direction to look for at least the first few steps of the search, and then you default to a default policy. Okay, so in that sense, the overall simulation policy is improving as you're doing more and more simulations. Okay. So each simulation consists of 2 phases, in tree and out of tree, as in like you apply tree policy first, get to some node. From that node, you kind of apply a default policy. The tree policy, your tree policy is basically an explore exploit policy. So you pick actions to maximize Q, or with some probability you don't. Okay. And in each, and then what you do is evaluate Q values using you get Q values using Monte Carlo evaluation. So basically averaging. Monte Carlo evaluation just means average out all the numbers, all the wins and losses that you got at that state. And then you improve the tree policy by doing epsilon greedy. Okay, so you don't bias always towards exploitation. You sometimes also do exploration. Okay, so it's basically simulation, but a little bit more intelligent simulation of how to pick the trajectories in your search tree. Okay. And it can be shown, and this is a technical result, again very similar to the Q-learning technical result, that if you do Monte Carlo research, your Q value at the root node, as in like the Q of S comma A, will actually converge to the true Q value at the at that node. Okay. Okay, so that was a tangent towards a little bit Go agnostic idea of Monte Carlo search and Monte Carlo tree search, or in general the forward search problem. Okay, now let's come back to the AlphaGo specific extensions. This part is going to be this part is from the Nature paper. So what does AlphaGo do? So AlphaGo essentially the software for solving this game of Go doesn't compute it's a planning problem, so it doesn't compute what to do in every state of the board. It only helps you it only tells you what to do in any given state. Okay, so it solves the forward search problem. It solves the forward search problem using MCTS. Okay, so AlphaGo is essentially doing MCTS. So there's no reinforcement learning yet in the picture. Okay, so you use MCTS as a Monte Carlo tree search for action selection, but it kind of uses two neural networks, okay, to achieve to do Monte Carlo tree search. Okay, so it uses a policy network and a value network to prune the search tree. So already there is a search tree and there is a particular trajectories that we're doing in intelligent way via Monte Carlo tree search here. But even with that Monte Carlo tree search idea, even though you're being intelligent and trying to pick only some experiences to figure out whether which action to take, even that is hard to do. And so AlphaGo uses two networks, a policy network and a value network, to further help in doing this research. Okay, so what is the policy network and what is the value network? We'll briefly mention. So policy network is just a given the state of the board. Okay, the board position is something like this. So you have a black stone here, white stone here, and so on. Given the state of the board, a policy network is just a distribution over where to place the next stone. Okay, so it's just saying, hey, place the next stone here or here with higher probabilities, and don't play the next stone anywhere else, for example. So policy network's output looks like this. Value network again is the same thing. Its input is the state. Okay, in this case, this value network is not the Q value network. It's just the value of being in a state. Okay, it's just a value function. So given the board state, it just says what is the what's the value of being in that state. So you just have a number which is between 0 to some 1. Okay, so it's just a higher number means higher valuable state, lower number means low value state. So here, because there's one state input, you're getting a number. Okay, so one number here. This illustration is not good, but it's basically showing one number output. Okay, which is the value of the state. So how do we use these two networks? The way we use it is okay. Let me just show the network. So given a state v theta of s, where theta is the network parameters. Okay, so is this this is what it looks like. And policy network exam, as I said, given a position, you have a distribution over actions to take. Okay, that's what a policy is. So and it'll have its own parameters, sigma. Okay, so theta and sigma are the parameters of these two networks. Now, how do we use it? This is the again search tree in a very illustrated way. So given some board position, there are all sorts of positions that can happen. Like you can place the black. You're black. Let's say you're the black, player, and so you can put the black stone here or there, and so on. So depending on that, a lot of things can happen. And eventually, somewhere, some victory, some loss, and so on. Right. So this is the full search tree. What you can do with Monte Carlo tree search is basically explore, exploit, have a tree policy at some point, and then a default policy some other point onwards, right? So by the end of the day, whether you use Monte Carlo tree search or whether you use simple Monte Carlo search, you have to get to one trajectory and get to the end to get a sense of, given that we did place a stone somewhere, what happened, right? That's what you're trying to answer. So instead of doing the simulation, what we do is actually two things. One is truncate the search tree. Okay, the search tree after, let's say, 10 levels or 20 levels, you don't look at what can you don't simulate all the way to the future. You just use a trained value network to say what is the value of being in that state. Okay, so let's say you read some board state, take that board state as an input, pass it to the value network. It will give you a value of how valuable that state is. Okay, so for that, of course, you need to have a pre-trained value network, and we'll talk about how to get that. Okay, so instead of simulating all the way to the end, we're just simulating up to some point and then using the value network to get a value, and that's what is kind of returned back to get estimates of Q values for being in a certain state and taking action and so on. Okay. Any questions here? Okay. And then we'll also use the policy network to bias our tree search part. Okay, so in the sense that, remember, we were supposed to do explore, exploit, and while exploiting, we had to maintain, we had to basically figure out which action to take by maintaining Q values. So that requires, either you can keep explicitly Q values, or you can actually just rely on a policy network, which will say, hey, given this board state, what action is promising, it'll already tell you. It'll give you a distribution of actions. So you can just follow that instead of basing it on Q values and explore exploitation. Okay, so So you can follow the follow the policy policy network directly. Okay. So but again, you need to have an access to this policy network first on the Q network on the value network. So how do we get that those two objects? So we train these two networks from supervised learning. Okay, so and reinforcement learning. Okay, so remember, so just to step back a bit, the original problem is just a forward search problem for the game of Go. We just need to solve what to do in a given board state, right? So that problem is not exactly a reinforcement learning problem. We said, okay, what to do in a given board state, we're going to solve using Monte Carlo tree search. Okay, to do Monte Carlo tree search, we still want to use some pre-trained neural networks. Okay, policy network and a value network. Okay, now the question becomes, how do we get this policy network and value network? And to get those objects, we're going to use supervised learning and reinforcement learning. Okay, so how is that? We'll look at historical data. Okay, and this is completely offline, not related to the game. So this is like before the game, before the AlphaGo event, for example. So we look at human expert position. So we know what is the board state and where did the human put the next stone, right? So given that, given the state of the board, where to put the next stone, given that x comma y pairs, you can just do multi-class classification. Okay, it's multi-class like 19 cross 19 locations where to put, and so you get an initial policy network already, which basically kind of mimics humans, right? So you get this policy network, and then you do and then what you do is use this policy network against itself and do what is called self-play. So in the sense that make a clone of the policy network, and one policy network is going to play the white player, the other one is going to play the black player, and now you want to sorry, at this point you kind of use reinforcement learning to improve the weights of one of these, improve the weights of one of these networks. Okay, so and that just uses reinforcement learning. In this case, since you're updating the policy network, there's a policy function gradient, policy functions parameters gradients that you're updating. Okay, so the important notion here is called self-play. It's basically you're playing against yourself, as in like the network is playing against itself. Okay, so the network is both playing for the white player and the black player. Okay, so with that self-play, you're going to generate a lot of data. So you can take a policy network, tell me what to do. Okay, you'll get some action. Now the the same policy network basically. Now if you are a white player, what to do? Take that action. So you kind of play against yourself, and you generate a lot of data. Okay, self-play data. What is the point of the self-play data? Because if you're doing self-play, you will eventually get to the end of the game, and so you know whether you won or lost, right? So that data, the self-play data, can be used to construct this value network. The value network, what does it need to say? Given the board state, trying to approximate what happened at the end, right? So with self-play, we know what happened in the end. Since we are kind of playing against each other. So given this problem, this is a regression problem. Given the board state, tell me whether the output is 0 or 1. 1 means black player won. Let's say 0 means black player lost. So you can predict that. Okay, this is a regression problem. Again, train it using gradient descent to learn this model. Okay, but the self-play also improves the policy network as well. Okay? So you can improve the policy network and estimate the value network. And with that, yeah. So I guess that same thing is mentioned here. So the policy network happens to be a 12-layer CNN. It starts with 30 million positions. So this is where I guess Korean Go Society 5+ Dan is the level, for example. So from human expert players, with this data, you basically learn it's just a network which is trying to predict the position. So multi-class classification problem. So some gradient, okay, to learn the parameters. So I guess at that time it took 4 weeks and 50 GPUs to get to some multi-class classification accuracy. Okay, here it's 57%, whereas previously it was 44%. Okay, so this is just classification here. Okay, initial network. Then we do self-play. So again, it's the same networks, same network from previous slide. So you kind of get again self-play between the policy network, and then you do a slightly different algorithm called policy gradient. It's not an algorithm, sorry, a policy gradient based RL approach. Okay, not the Q-learning stuff that we saw. to change the weights again. Okay, so to learn the weights such that it can play against itself and can win. Okay, so so that's the update, and again it took some 1 week and 50 GPUs to do this. So so how do you check, right? So whether this thing is actually working or not. So whatever is the final policy, if you play that policy against the initial policy network, it actually wins 80% of the time. Okay, so so it can do well is what they're trying to say. Next is the value network, which is again very similar to the policy network. It's producing a regression output, a single output, and so it trains on 30 million games of self-play. So these are like 30 million games. So going from starting to end, and every state, what's the final situation that happened, and so you just solve the square loss, basically mean square error. And so this is just a regression problem, actually. Yeah, this is a regression problem, so no reinforcement learning. So you just take the so square loss exactly produces this. We saw this at the beginning of the lecture, right? Again, it took about these many GPUs and a few days to solve this. So this was actually an important contribution. It is a position evaluation function, right? So whether your position as a board state, are you good or not? It's hard to evaluate that because you don't have access to some high quality data, with full end of the games to do that. But it was able to do that. So this network kind of really helps do the search within like a minute or within whatever the search budget. Remember, with forward search problem, if I tell you there is no search time limit, then you can keep evaluating everything and you can do hundreds of simulations. But if I tell you have to come up with an answer within 2 minutes, then you can only do some amount of simulations, right? So having such a network, so that you don't have to evaluate all the way to the end of the game is useful. Okay, so yeah, let me not mention about the MCTS again, but you're welcome to look at it offline. But basically, the tree search procedure has 4 phases: selection, expansion, evaluation, and backup. We didn't explicitly talk about all these steps, but the idea is, as I said, just not using the default policy all the time, but kind of doing explore exploit incrementally at the beginning and then doing some default stuff later. Okay. Okay, with that, I guess they won. They won back in 2016, and now actually the software is much better. But so that was I guess the kind of engineering or the setup of the agent behind the scenes. So RL is just one part. Okay, it only comes up in the self-play part. There's 2 supervised learning steps, and also the Monte Carlo tree search, or the solving the forward search problem, which was needed to kind of achieve that milestone. Okay. Any questions at this point? Okay, so let me just summarize. We are kind of ahead of time, but so what we've seen today is function approximation, case study with DQN, which is also part of your assignment, question number 3, and also a case study with AlphaGo. Okay, so and we also introduced as a part of AlphaGo, we also introduced the forward search problem, simple Monte Carlo search and Monte Carlo tree search, at least informally. But I'll summarize, for all the previous 2-3 lectures about RL. RL is a framework to make, software agents intelligent. Of course, it relies on a particular strategy. Especially, first of all, it only applies to sequential decision making. So you have to have long-term consequence of you doing something, and you doing something in a state influences the next state, and so on. So RL is basically a trial and error method, but the trial and errors the trials that you make is adaptive. It's going to be based on previous errors you made, and so you're going to be intelligent, and so you're going to be given the reward signals, you're able to better and better match accumulate more reward signals. Okay? So that's the approach. So you just have to specify goals and provide feedback, the reward signal, compared to supervised learning. Now, vanilla RL, as in the RL we saw up to last lecture, is not scalable because there was no function approximation. So Q-learning, for example, is not scalable beyond the toy problems. Okay, if you have 10 states and 10 actions, already you have to estimate like 10,000 numbers, and so you need to do a lot of simulations to do that. Function approximation lets us manage scale, and that's where we saw that the number of states can be anything now. It doesn't have to be finite. But so far, at least in today's lecture, we've been only looking at number of states blowing up, not the number of actions. You can also blow up the number of actions, as in the actions can also be infinite. But then the solution approaches, we have not seen it, but there are others. Okay. So it complements deep learning that solves more of a forecasting or a perception problem, whereas RL is more focused on decisions, okay, actions and their values. And so DQN, we saw a couple of interesting ideas: experience replay and freezing of Q targets to stabilize learning. And AlphaGo, we saw forward search and multi-color research with approximations. Okay. There's still a lot of challenges in this technology, and that's why it's, I guess, not super mainstream, but it is becoming more and more applicable. For example, it can be used for recommendation systems, which, for example, for Netflix and things like that, where you take some action, there's going to be some feedback in terms of content consumption or whatever, and based on that, you update your queue network and so on, and then do better actions later. Okay. So it has applications beyond just games domain. In fact, if you have an MDP problem, you can always ignore the full MDP information and still solve for the best policy using RL. Okay, so if you're lazy and you don't want to use Q learning, or if you don't want to use Q validation and things like that, then you can always use an RL like DQN, for example, to solve an MDP problem as well. Okay, which has applications in supply chain management and other areas. Okay, so with that, let me end. Okay, this was a video, but I don't have the video right now. But we saw the Tesla video before, I guess. So with that, let me end for this content. Just to wrap up. Yeah, I'll just wrap up the list of topics we saw, and then because next week we are going to be looking at projects, and so the next couple of weeks is going to be project focused. I mean, we'll revisit these topics in each of the projects, but then what we've done so far is in this course mostly looked at a few supervised learning architectures, and then a couple of unsupervised learning architectures, and then reinforcement learning. Okay. So what are the supervised learning architectures? We started with feed-forward networks, and then looked at convolutional neural networks, CNNs for images. Then we saw word-to-vec, which is not very specific to NLP. Okay, you can actually use it for even other things like recommendation systems and so on. Okay, any other sequence problem. So as long as you're instead of words, you can have other objects. Okay, and still you can use word-to-vec. And then we saw recurrent neural networks, so LSTMs and GRUs and things like that. Then we saw transformer-based architectures, which are kind of very popular these days. Can again be used in recommendation systems. I keep giving the same example, but beyond NLP, for example. And we saw the notion of attention, encoder-decoder attention, and then self-attention. Then for unsupervised learning, deep learning architectures, we saw two. One is called variational encoder, and then the other one is called a generative adversarial network. Variational encoders that we saw, and both GANs and VAEs that we saw were specific to images, at least in our discussion, but both have been extended beyond images. Okay, so for example, VAEs can be used with graphs. Okay, and they are called graph VAEs, and there's actually a PyTorch library called PyTorch Geometric, which you can try it out, where you can encode and decode graphs. Okay, and so you can compress a graph to a latent space and then bring back the graph using decoding. Okay. So that was about deep learning, and then we switched gears and started talking about bringing in discussions about decision making. And so in particular, we were looking at sequential decision making. And so we started with A/B testing as it's not really sequential. It's a kind of doesn't exploit any sequential nature. We started with multi-arm bandits and then contextual bandits, and we differentiated that with supervised learning, as with the idea of bandit feedback. You only know what you did. You don't know what would have happened if you did something else, right? That's not that's different. And then we saw basics of reinforcement learning, so policies, state, action, value functions themselves, and models. We also saw briefly Bellman equations, and then the Q learning algorithm. And today we saw function approximation, which can allow Q learning to scale, for example. We saw a couple of more ideas, experience replay and target freezing, which go into this deep Q network algorithm. And then we saw multi-color research briefly, informally, for the AlphaGo case study. Okay. So a lot of topics over the past few lectures. Next, we'll do individual meetings with groups, and then we'll have a presentation which is going to be on Zoom. Meetings are also going to, meetings are also going to be on Zoom. Okay. So I guess that's a roundup for this the set of topics. If you have any questions, just reach out to me. I'll end the recording now.